Welcome back everyone. We are in the process of learning about programming using the C programming language, and currently we are in the unit called as pointers. We have already covered the basics of pointers. We have already covered some of the arithmetic operators that we can use on the pointers, and now in this lecture we are going to learn about how pointers and array, that is 1D array, are interrelated and how it works together. The topics to be covered in this lectures are pointers and 1D array. Right? What is the relationship between the array, 1D array, and pointer that we are going to cover in details. How we can access the array elements using the pointer notation. We are going to learn some new tools to access the array elements, that is using the pointer notation. And finally, we are going to find out or differentiate between the subscript, array subscript notation and the pointer notation. So let's get started. Now, first of all, before we start, let's learn about something called as the scalar and the vector quantities. You may have already heard about these terms, scalar and vector. So here you see I've declared one integer variable called as a, and I've assigned the value 5 to this variable a. Now this variable a can only hold a single value, isn't it? Here it is holding the value 5. It can hold any other value, but it can only hold a single value at a time. Therefore this variable a is called as a scalar variable because it can hold only single element or single entity at a time. Okay, so a is a scalar variable. Now whenever I declare this variable a, what happens inside the computer's memory is that it is going to allocate number of bytes for storing this variable a, that is the value 5 in the variable a. Okay, so a is a container wherein I'll be storing the variable 5. So a would be occupying this space. Here you can see in the diagram, right, a is occupying this yellow box starting from the address 1000 to address 1003. So here I am assuming that integer is taking 4 bytes of memory, right? So 1000 is the first byte, 1001 is the second byte, 1002 is the third byte, and 1003 is the fourth byte. So it is occupying 4 bytes in the memory and its starting address is 1000. Okay, so if I print a, what happens? If I just write printf %d and then print a, I just write a, it will give me the value of a. And what is the value of a? What is inside this box? Inside this box the value is 5. The variable a is storing the value 5, so it is going to print 5. So 5 is the output for this particular printf statement. Now let's move into something called as an array, which is the topic of interest for us, right? So here I have declared the variable b, right, and it is holding 3 elements 1, 2 and 3. Now what happens inside the computer's memory is that it is going to allocate the space for the contiguous memory space for me to store 3 integer variables. I've already told you integer takes 4 byte. So 4 byte for each value, right? So for 1 it will be needing 4 byte to store 1, 4 byte to store 2 and 4 bytes to store 3. So in total I'll be needing 4 plus 4 plus 4, that is 4 times 3, that is 12 bytes in total. So in the computer's memory, it is going to allocate 12 bytes for me. Here I am assuming that the starting address is 1000. It can be anything. Here I am assuming that it is 1000, right? So what would be the starting address would be decided by the operating system and the compiler, right? Here this is just my assumption that it is starting address for this particular variable b is 1000, right? So you can see here it is from 1000 to 1003 is allocated for the first value, that is 1. So 1 would be stored in the address 1000 to 1003. I've taken 1000, 1001, 1002 and 1003, 4 bytes because integer occupies 4 bytes. In this example I'm assuming that. Okay, so starting at 1004 address, 1004, 1005, 1006 and 1007, it would be storing the value 2. Okay, and starting from 1008 address, 1008, 9, 10 and 11, it is going to store the value 3. Okay, each of this value is going to have a unique index also. Like at index 0 I have value 1, at index 1 I have value 2 and at index 2 I have value 3. This is how it is going to be stored in the memory. Now the very interesting part is in the previous case, the scalar variable a, right, I just did printf %da and I could get the value of a, that is 5. Now here this is not a scalar variable, b is not a scalar variable, right? Because b is not just storing a single value, it is storing multiple values together, right? It is storing 1, 2 and 3 together. The list is stored, right? So this is called as an array. So array is a vector. It's a vector quantity. Okay, so A is a scalar quantity and B is a vector quantity. Now in the first printf, I was just trying to print A. By just writing A, I could get the value of A. What happens if I just write printf %db? Is this a valid statement first of all? If it is valid, what would be the value? Would it print the entire array? Or would it print the first value of the array, that is 1? Or what would it print? What do you think? So when in doubt, just open up your compiler and try to write your code and execute it and see what happens. Okay, so let's try to execute this code and see what happens. Alright, so this is a very simple program that I'm going to create, right? So I'm having this variable b, like in the case, which can hold 3 values here, right? The values were 1, 2 and 3. I'm just writing the same code here. So what I'm planning to do is I'm just trying to print the value, right? I'm just trying to print the variable b, right? Now we know that b is a vector quantity, right? What happens if I print b? Now let's see, first of all, would it give me any error, right? So to test that, what we do is we first of all compile this code and see what happens, right? So let me try to compile this code by writing gcc space pointer and array.c, right? So it is telling me some few things are giving here, right? That is line number 1, that there's no hash include stdio.h. I'm using printf. There's no header file included for that, so I have to do that first, right? stdio.h. Compilers are our friend. They are giving us the error message, so save it, right? Now let's try to again compile this. Yeah, so there is no more warning or error coming up, right? I think it looks good. So let's try to execute this. A.exe, right? So let's print. So first of all, the thing to note down here is this is not giving me any error, right? What would it print if I execute this code now? Let's see, hit enter. Now it is giving me some value, right? 1254095652. You may be wondering what this value would be. This isn't any random value that's coming up. It is not a garbage value. Okay, it actually is the value. This value is nothing but the address of the array. Now whenever I print b, it is actually printing the address of the array b. Okay, so I'll just give it as a comment here, address of array b. In that example, I was assuming that the starting address was 1000, right? But here the address is 1254095652. As I already told you that this address is allocated by the compiler and the operating system. So in my case, this is the address that is being allocated. And in that example, the address that we allocated was 1000. Now let's get back to our screen and see what is the output in that case. Now in this case, you could guess the answer. The answer would be 1000. If I just print b, it is going to print the starting address of the array, because array is having many addresses, right? 1000, 1001, 2, 3, 4 up to 1011, isn't it? But it is going to print the starting address of the array, or the address of the first element. The first element is 1. The starting address of the first element is 1000, so it is going to print 1000. So if I print b, it is going to print me the address. That is the very important point you should note. So by performing this experiment, we have concluded that by printing the name of the array, we're getting the address, right? So our first observation is name of the array is nothing but the address, right? We have got the address of the array. In this case, we got 1000, right? We got the address. 1000 is the address. It is the address in the memory location, right? So name of the array is the address. Now you may be wondering, address of what? This address belongs to whom, right? This address 1000 belongs to, this is actually the address of the value 1, address of the first element 1, right? Now first element 1 is having actually 4 addresses, 1000, 1001, 1002 and 1003, because 4 bytes. Each byte is going to have a unique address. I've already told you that, right? So 4 bytes, but 1000 is the starting address, right? So it is, what is the address? Address of what? It is giving the address of the first element. The first element in this case is 1. The starting address of the first element is 1000. Now name of the array. So we can say that name of the array is the address. Now address is nothing but the pointer. So now I can say that name of the array is the pointer. So here name of the array B is the pointer. So this is the conclusion that we are reaching at. Now what if B is a pointer, we should be knowing what is the type of this pointer, right? Is it pointing to a float? Is it pointing to a character? Is it pointing to an integer? Right? What is the type of this pointer? And the answer is very simple. The type of this pointer is the integer pointer, because it is having the address of the integer. It is actually holding integers, right? So it is going to have the address of the integer, because first element is 1. 1 is an integer, right? All these elements are integer. So 1000 is the address of an integer, right? So what is the type of the pointer? It's a pointer to an integer. Now a very important question that comes up is, now if B is a pointer, we have already learned in our previous video, previous lecture, if B is a pointer, if there's a pointer, we can perform many pointer operations, pointer arithmetic. We can actually do B++, right? We can actually increment the pointer, right? We can actually decrement the pointer, right? We can advance the pointer forward and backward by incrementing and decrementing. All these operators we have already learned in the previous lecture. Now if B is a pointer, can we perform any arithmetic operation on B? Right? We don't know the answer, right? So what do you do? If you don't know the answer, open up your compiler and try executing the code. Let's see. Okay, we are back into the code. Now what we are trying to do is we are trying to perform some arithmetic here in the pointer, right? Perform what arithmetic? Pointer arithmetic to this, right? How do you perform the pointer arithmetic? I can just write, let's say, if B is a pointer, I can write B++, right? This is a pointer arithmetic. Let us try to compile this code first. Compilation is there, right? Now while compiling this code, we got an error that, the L value is required as increment operand, right? So it is not allowing us to increment the pointer B. We said that B is a pointer, but B is actually an array, right? Because it was giving us the address, so we told that B is a pointer. Right? If it is a pointer, it should actually allow us to increment the pointer, right? But it's not allowing us to increment the pointer. That means this is a pointer which is a constant pointer, right? It is a constant pointer. So constant pointer cannot be incremented or decremented, right? So B is an array, right? So B, that is the name of the array, is a constant pointer. You know what is a constant, right? Constant cannot be modified. It is just read only, right? So B is a pointer that cannot be modified because B is an array. If you modify the array, now that array would not exist anymore. So let's go back to our screen and see more on this. See, the reason why it is not allowing us to increment the pointer B is an array B, is because if I increment this, now B becomes, let's say if I am allowed to increment, B was initially 1000. If I am allowed to increment and go to the next position, now if B somehow becomes 1004, now the thing is this, the array has entirely changed. Previously the array was this entire 3 elements together, right? Now once I increment B, now the array is this 2 elements only. So I have actually modified the array itself. That should not be permitted. So therefore you cannot actually increment B, because B is a constant pointer. So array name is the constant pointer here in this case of integer type, which is holding the address of the first element. So we got that point in. Now let's try to quickly revise. We have already noted down that name of the array, any array for that matter, is a constant pointer. It's a pointer, but it's a constant pointer. Okay, the constant pointer is the pointer that cannot be modified, and that pointer points to a memory location, because pointer will be pointing to a memory location, right? Of whom? Of the first element in the array. So in this case, B would be actually 1000. It is holding the address of the first element, starting address of the first element. Okay, in this case, if I print B, it is 1000. Now let's try to create some other pointer. In this case, you see, I write int star C. So C would be a pointer variable, right? So C is a pointer variable of type. This is a pointer to an integer. So I can write this is a pointer to int. It is a pointer to an integer because int star C. Now what do I do is I try to assign the address of B0, ampersand B0. So what is B0? B0 is the first element 1. What is the address of the first element is 1000. I'm trying to assign 1000 to C. So 1000 is assigned here. Now I can say this variable C, or the pointer variable C, is holding the address of the array, the starting address of the array, which is 1000. So I can say that C is now pointing to the array because C is having the address of the array B, right? Now if I can write C equals to ampersand B0, I've already told you that ampersand B0 is the address of the first element and B is also the address of the first element. So instead of ampersand B0, I could also write B. So I can write C equals to B. So C equals to B is equivalent to C equals to ampersand B0, because ampersand B0 is the address of the first element, which is 1000, and B is also the address of the array, which is nothing but the address of the first element, which is again 1000. So ampersand B0 and B are the same. So now you may be wondering, here we have two pointers. One is B and one is C. B is the name of the array, which is a constant pointer, and C is a pointer that we have created on our own. Right? Now what is the difference between the pointer B and pointer C? Pointer B is the name of the array and pointer C is our own pointer. Now it's very simple. We have already noted down that pointer B is a constant pointer. That means no pointer arithmetic is permitted. Pointer arithmetic is not permitted on B. So you cannot do B++. You cannot actually write B is equals to B minus 1. All these things are not allowed because B is a constant pointer. But C is not a constant pointer. We have created this pointer. This is a normal pointer. This is non-constant pointer. So in this case, we could very well do C++ is allowed, right? C++ is a programming language as well. Okay, it's a very interesting, very nice programming language, the advanced version of C, wherein you have the concept of object-oriented programming. We are not talking about that programming language C++, but the variable C here is a pointer variable. If I do C++ now, it is a valid operation because C is a normal pointer. It's a non-constant pointer. So pointer C is a non-constant pointer. All valid pointer arithmetics are permitted. So you can perform all the pointer arithmetic. Now let's try to learn about the array subscript and the pointer notation. What is the difference and how are they related? Okay, so first of all, again the same example I've declared the variable B, an array B, right, which is holding 3 elements 1, 2 and 3. In the memory it is occupying the space as shown here. At index 0, 1, that is the starting address is 1000. At index 1 the value is 2. At index 2 the value is 3. Now I'm going to just give you this printf statement. Printf b1 equals to %d. I'm trying to print b1. B is an array. This is the array B. At index 1, what is the value? b1 is this one, right? This is b1, isn't it? So b1 is nothing but 2. Your guess is absolutely correct. At index 1, the value is 2 in this array. So I'll get the value 2 as the output, which is very easy. Now let's make it more interesting. What if instead of b1 I print 1b? Is it allowed? 1 is not an array, right? So I've just interchanged the position of b and 1. b1 now becomes 1b. Is it a valid statement? Is it allowed? We don't know, right? When in doubt, we have to investigate. So let's investigate by writing the code. Okay, so in this code, I'm trying to print 1b, right? That is what I wanted to do, right? That is what I wanted to investigate, right? So I'll just write printf, right? 1 subscript b equals to %d, and I'm just going to print 1b like this, right? Now, first thing first, is it a valid statement? Will I get any error? What happens? We don't know, right? Let's try to compile this first. And oh my god, no errors, right? So 1b is a valid statement. There's no mistake in this, right? It is working perfectly fine. No errors right now, isn't it? Let's try to, just predict what would be the answer, right? Let's try to run this code ./a.exe, and I get 1b is equals to 2. Oh, I'm getting the second value, it seems. What is b1? Let's see what is b1. b1, let's compile this again and then see what is b1 and what is 1b. Are they same? So this would be b1. b1 is also 2 and 1b is also 2. So that means they are the same thing. So b1 and 1b are same thing. How is it possible? Let's try to see now. So our question was how? How is it possible? How is 1b and b1 equivalent? 1b also is 2. b1 is already 2. How is it possible? Right? Now to understand this, to know this, we should understand how the array subscript notation is processed internally. Now array subscript, you know what is subscript, right? So this is the subscript notation. If I write b1, how is this processed internally? The same way 1b would be processed internally. So internally all these things will be treated as a pointer. It will be dealt in a pointer notation, right? Not in a subscript notation. So to understand this, let's take few examples. You know what is b, right? Can I say that b and ampersand b0 are equivalent? B is the starting address, right? In this case 1000. Ampersand b0 is the address of the first element, which is still 1000, right? So I can say that ampersand b0 and b are equivalent. Ampersand b0 and b are equivalent. Now the next question is, if ampersand b0 and b are equivalent, can I say that ampersand b0 is equivalent to b plus 0? Because b plus 0 is b, right? B plus 0 is b. So I can say that ampersand b0, that is address of the first element 1000, is equals to 1000 plus 0, which is still 1000. So similarly, I can say that ampersand b1 is equivalent to b plus 1. Similarly, ampersand b2 is equals to b plus 2, and ampersand bi, I is any index, would be b plus I. Let's see how it works. Okay, so here I have told you that ampersand bi is equivalent to b plus I. We are taking the same example wherein we have got an array b with 3 values 1, 2 and 3. Starting address is 1000, right? Address of the second element is 1004. Address of the last element is 1008. We already know that ampersand will give you the address of the element, right? Address of the variable. So if I write ampersand b0, I'll get the address of the first element, so I'll get 1000. Similarly, if I write ampersand b1, I'll get 1004. Ampersand b2 would give you 1008, right? And ampersand b0 equals to b plus 0, right? Now let's take this, the second one. We are telling that ampersand b1 is b plus 1. Let's see what is b plus 1. B is the address of the first element. What is the address of the first element? That is 1000. What is 1000 plus 1? 1 is just the offset. We have already discussed this. So if I have to get the address of the next element, I have to multiply by the size of the data type. Here the size of the data types, integer is 4 bytes. So size of integer is 4 bytes. So I multiply by 4. So 1000 plus 4 is 1004. So I get this address 1004. So ampersand b1 is b plus 1. You can still try. What is b plus 2? B plus 2 actually is 1000 plus 2 times 4. So this is nothing but 1008. So b plus 2 is 1008, which is equivalent to ampersand b plus 2. So in general, what we can say is very simple. We can say ampersand bi is equals to b plus I. Right? So this is the subscript notation. This is the pointer notation. Because b is a pointer, right? So b plus I. So b plus I is same as ampersand bi. Okay. Now let's look at how we can access the value of that particular address. Right. So 1, 2, 3 are the values stored in this array, right? In the location 1000, 1004 and 1008. Right. So how do I access this value 1? We just directly write the name of the array, subscript, index of that element. So name of the array is b, subscript 0. At index 0, I've got the value 1. Similarly, how do I get this value 2, access of this value 2? Array name b, index is 1, b1 is 2. Right? So how do I get the access of the value 3, I write B index 2. At index 2 I've got the value 3, so B2 is 3. Now we have already noted down that B plus 1 would give you the address of the element at index 1. At index 1 the address of the element is 1004, right? B plus 1 is nothing but 1004. Now if I want to get something, the content inside that address, in pointer notation what do? We use the indirection operator, right? So if I write star B plus 1, B plus 1 is the address. What is there inside this B plus 1? If you want to get that, you have to use this asterisk indirection operator. So star B plus 1 would be what is there inside this address 1004? That is 2. So star B plus 1 is 2. So if I want to access this value B0, the value 1, you write star B plus 0. So what you can conclude now is that, BI is equivalent to asterisk B plus I, right? So BI is equivalent to asterisk B plus I, and ampersand BI is equivalent to B plus I. So these are two important things, right? How do you convert the array subscript into the pointer notation? This is what you should keep in mind. Now to understand this in more details, let's try to take this example wherein we have actually declared this array, right? ARR, integer array, having following 8 elements, right? So in the memory, it is going to occupy this space. Let's say the starting address here is 100, right? So the first element is having the address 100 and each integer is 4 bytes long. So 100, 101, 102, 103. 4 bytes is stored, reserved for the first element. So that is index 0 element address is 4 bytes, 1000 to 1003. So similarly, the last element is having the address 128 to 128, 129, 130 and 131, 4 bytes. Okay, so this is how this array looks like. Now in this array we can just write down, as in the previous case, that ampersand ARR I is equivalent to ARR plus I, and ARR I, the value, is equivalent to asterisk ARR plus I. Okay, now in this example let's try to take some statements, the programming statements, and then see what is the output. Let's try to predict the output. Okay, so first of all I'm creating the pointer P, right? P is a pointer, integer pointer, which is having the address of ARR2. What is ARR2? ARR2 is this one, right? 3. What is the address of the element 3? So this P, the variable P, is pointing to where? 1000, not 1008, it is 108. So it is pointing to 108. So P is the pointer which is holding the address of the element at index 2. So P is 108. So what happens if I write star P, asterisk P? Asterisk P is what is inside P. Asterisk P, P is a pointer. What is inside P? Inside P, inside 108, the value is 3. So asterisk P is equivalent to 3. Okay. Now P is a pointer, right? Can I write P1? Can I use the subscript notation on a pointer? Very well, you can use that. What is P1? So this is 108 is P0, right? P1 is what? It's P plus 1, isn't it? Right? So I have to use asterisk also because I'm trying to get the value, because I'm using the subscript notation here. So star P plus 1. P is 108 plus 1. 108 plus 1 is 112. So what is inside 112? Inside 112 there is minus 6. So I'll get P1 as minus 6. Now what is P plus 5? P plus 5, P is what? P is 108. 108 plus 5 is not 113. I have to write 5 into size of int. So 108 plus 20, that is 128. This is P plus 5. Okay, so this is P plus 0 or P, this is P plus 1, this is P plus 2 is 116, P plus 3 is 120, P plus 4 is 128, and P plus 5 is, P plus 4 is 124 and P plus 5 is 128. So P plus 5, the answer is 128. It is a pointer. Okay. Now, what is star P plus 5? It's very interesting. Star P plus 5. Now there are two operators, plus and asterisk. Which one do you perform first? So if you look at the precedence, star would be performed first, right? In direction operator. So first you perform star P. P is 108. Star P is the value inside this address 108. Star P is nothing but, star P was 3, right? So 3 plus 5 is nothing but 8. Star P plus 5 is 8. It is the value. Star P plus 5 would not give you the address. Okay. Now what is star P plus 5? So I've inserted P plus 5 in a bracket. Right. So first of all, P plus 5 is executed. So what is P plus 5? We've already seen P plus 5 is 128. Star of 128. What is inside this 128? Inside 128's address, the value is 14. So this would give you 14. And then finally, I've taken a very interesting example. Can I write P minus 1, a negative subscript? Is it possible to have a negative subscript? So P minus 1 is nothing but, this is allowed, right? So this is nothing but star P minus 1. Star is a star, asterisk. P is 108. 108 minus 1 is not 107. I have to write minus 1 into 4 bytes. So this is star. 108 minus 4 is 104. What is there in 104? So I'm just going, one step back, right? So if I go to 104 address, I get the value 8, right? So here the value 8 is printed. Okay. So by doing this example, I hope you have understood how, pointer notations can be used in an array, particularly in a 1D array. Later we are going to see how to use this on 2D array as well. Okay, it is just the extension of the same thing. Okay, now let's try to write a small program or modify a program that is written using array notation using a pointer notation now. Okay, let's do that. Now this is a program wherein we are supposed to convert all subscript notations to pointer notations. Let's read line by line, okay, and see how we can do the conversion. Okay, so first of all, declaration, we'll leave it line number 8 as it is. So it is trying to get the number of elements. So this is an integer variable. So this is a %n itself is a pointer, right? So therefore I use %n. I need the address whenever I'm taking the input. No changes here, right? Now can I change this? Can I just change this %ai? I can change this, right? Because we know that %ai is equivalent to a plus I. So I'll write, instead of %ai, I'll write a plus I. It is the same thing, right? And let's come down. So in the for loop, I'm just trying to access the element, the value of that array, right? One by one by using the indexing, subscripting. We also know that ai, how do I get the value? We know that ai is equivalent to a plus I, and inside the bracket, right, I give asterisk a plus I, right? So instead of ai, I'll write star a plus I. So this is a program actually to find the sum of elements in an array. So that's all, right? I've just done all the changes, right? So let's try to compile this code and see if it works well. Okay, gcc subscript, so no error, right? a.exe, and number of elements, let's say 5. The values are 1, 2, 3, 4 and 5, and the sum is 15. It works fine. So in this lecture we learnt about array and pointer, how 1D array and pointers are interrelated, right? And how we can use the pointer notation instead of subscript, array subscript notation. Using a pointer notation makes your program a little bit faster because there is no conversion happening. If you write the subscript notation, that would be converted first to the pointer notation internally and then executed. But if you directly write using a pointer notation, there is no conversion, internal conversion happening. Therefore, your program becomes a little faster than the previous one wherein you have used the array notation. So this is all in this lecture. We are going to meet in the next lecture. Until then, stay tuned. Thank you.